Hello, my name is Jennifer Giggy, and I'm the Packaging Department Scientist at Nelson Labs in the Salt Lake City location. Today, I'd like to talk to you about one of our newer test offerings, mass extraction. Mass extraction is a CCIT or CCI test. It's a container closure integrity test. These are tests that are designed for rigid containers, such as vials and syringes and bottles. CCI tests are often used in place of traditional sterility type tests to show that the containers are sterile and will remain sterile throughout the expected shelf life. Why would you do CCI testing? Well, ISO 11607 says that drug and device packaging must remain sterile until the point of use. Well, if your package is a pouch or a tray, you'd use maybe a bubble emission test or dye migration test to show package integrity. But if your packaging is a glass vial or a syringe, then you'd use a CCI type test to show package integrity. There's also a requirement that drug products maintain their purity. Some drug products are sensitive to air, and air molecules being smaller than microbes, in order to ensure that no air can enter the container, we need a test with a really small defect size. Bubble emission test can detect about a 250 micron leak. Dye migration test it's a little more sensitive. It's about a 50 micron leak size. But most of the CCI tests are capable of detecting leaks that are 10 microns or smaller. So a CCI test would show that both these requirements, sterility and purity, are met. CCI test methods are divided into two groups. The first group is probabilistic methods. These are methods where the result is a pass or a fail, and they're based on observations. The second group is deterministic methods. These are methods where the result is a measured number that can be compared to a standard value. In other words, my result of X is either higher or lower than a pass-fail threshold value. Above the number and the result is a fail. Below the number and the result is a pass. So which type of method should you choose? Well, all the methods listed on the table on the previous slide are commonly used in industry. Now, some choices as to which method to use are based on preference, and some are based on limitations of the test sample. The latest version of USP 1207 recommends deterministic test methods for CCI testing. This is driving a shift in the industry towards deterministic methods. You can see why deterministic methods are preferred. They're giving a measurement, which not only tells you if you passed or failed the test, but also how close or how far from that magic pass-fail threshold you are. Did you just barely pass the test, or did you fail it miserably? Deterministic methods they're also usually non-destructive, which allows for 100% inline testing during the manufacturing process. Well, this is especially useful since most typical failure rates in vial and syringe containers are very low and not likely to be detected unless large numbers of samples are tested. If you have a very sensitive product and air contamination can change the chemical formulation of that product, well, even a single failure in a million could be disastrous. 100% inline testing for a laboratory setting, this non-destructive thing means that failing samples can be, retested or investigated for failure cause. The smallest detectable size is usually much smaller with deterministic methods. In contrast, probabilistic methods are subjective. You're relying on a human to make a judgment call versus a machine to measure a value. Probabilistic methods are more prone to contamination because the container usually needs to be opened in some way during the test. This is what makes those tests destructive. Finally, as we discussed earlier, the minimum defect size is usually larger for probabilistic methods. So the choice is pretty clear. Use a deterministic method wherever possible. So which deterministic method, remember there were quite a few on the list, is the best option? Well, this depends on a lot of factors. Each method has advantages and disadvantages. For example, a laser headspace is fantastic for containers packaged under alternate atmospheres. But if you package with ambient air, Then you would need to condition the samples in nitrogen or some other gas prior to testing, and well, that adds some time and expense. Another great example would be HVLD. This is great for detecting cracks or holes in the glass vial, but it's not as good with the cap to vial closure. So you want to find a method whose advantages match your application. For Nelson Labs, we were looking for a method that was well suited to a wide variety of product types. Because as a test lab, we test all kinds of samples. We also wanted something that was easy to execute, fast, and reliable. Oh, and of course, we wanted a method with great sensitivity. Can you guess which one we chose? Mass extraction is based on the mass conservation law. So this law states that the mass flow will not change in a closed system. If you measure the makeup air required to hold a vacuum in a closed system, then that equates to the leak rate. The leak rate is quantifiable and it correlates to the defect size. So if I have a smaller leak rate, then I have a smaller defect. A larger leak rate would be a larger defect. The leak rate can be influenced by a number of factors. The biggest one is the amount of free space in the test chamber. And it will change slightly from one configuration to another. So there isn't a single flow value that equates to a certain size defect. This would need to be determined with each test setup. The flow rate is, however, consistent using the same test setup repeatedly over multiple days. So for an example, if my product is a 20 ml fill vial, the leak rate I determine equates to a 2 micron defect will be relatively consistent from day to day. But if I switch to a 10 ml vial, now that's a smaller vial, so now we have more free space, and I use the same test chamber, then I would expect my leak rate for the 2 micron defect to be slightly different. So what is mass flow? Well, it's actually very similar to volumetric flow, which is more commonly understood. Volumetric flow is a volume change over time, and it's usually expressed in units like centimeters cubed per minute. Where mass flow is a mass change over time that would usually be expressed in units like grams per minute. For mass extraction, the flow rates are expressed in micrograms per minute because the mass extraction detector that we have is capable of measuring to that sensitivity. So to review, the output or results for a mass extraction test are flow values in micrograms per minute. So it's a flow value, but it's measuring mass to determine mass flow. Here's a bench version of a mass extraction instrument from ATC, or Advanced Test Concepts. They're the company who pioneered the test method and the technology. Most the mass extraction instruments that they make are custom built for inline manufacturing, but ATC does offer this bench unit for laboratory or QC testing. You can see the test chamber on top of the instrument. This particular chamber is designed for vials. There's also a pump to the left. There's a display in the center of the unit, which shows all the critical test information, as well as the mass flow graph. Of course, this machine's off, so that shows nothing right now. This instrument will operate as a standalone unit, or you can operate it through a computer. ATC offers a 21 CFR Part 11 compliant software package. We have that here at Nelson, and we use that for all of our testing. The software package controls the user access and secures the data and tracks the changes. Let's look at what we need to run a test. The first thing is we need a test chamber. The chamber is connected directly to the instrument. We have a few chambers for different size sample types. Here's some pictures. In the slide, we have a vial, a syringe, and an auto-injector chamber. The open picture of the syringe chamber shows the little O-ring that's used to seal the chamber when the vacuum is drawn. Each chamber is designed to fit a specific shape and size. Next, we need a master. The master is a solid metal part that's similar in size and shape to the test sample. Because it's solid metal, we know it has no leaks. We use the master to verify the test system is clean, dry, and free of virtual leaks or residual mass. If the master does not pass the test, then this indicates there's something wrong in the test system that needs to be removed or fixed before the samples can be tested. The master is our positive control for the test, and it must show no leaks in order for the test data to be valid. We have a library of different masters, and all these you see in the picture will fit into one of those test chambers. Finally, we need some void fill. I discussed a little bit earlier that free space in the chamber will affect the test, so we want to minimize the free space as much as possible. These void fill parts are also solid metal, so we know they have no leaks. And the void fill and chambers are designed by ATC with special evacuation channels to help draw out all the air as quickly as possible. We have a variety of different filler options for each chamber, so we can test a variety of sample sizes with each chamber. For example, the vial chamber has 8 different vial master parts with corresponding filler parts. In this way, we test most routine vial sizes with the same test chamber, and we can still minimize the free space. The CLO, or Calibrated Leak Orifice, is a defect of known size that's incorporated into the instrument. It's made by encasing a glass microcapillary of a known size into a housing that's connected directly into the instrument. There's a switch on the front of the instrument that turns the CLO on or off. Think of it like an old train. When the switch is off, the train goes down the normal track. When the CLO switch is turned on, it's like that guy in the movie on the side of the track who's pulling on that rail, and he has to hurry and pull that switch so that the train gets off the track so it doesn't crash into an oncoming train or something. So when he pulls that switch, then the train goes over onto the spur track, and that's kind of like the way that the CLO works. So if the CLO is on, the test goes off that normal path through the CLO, and that makes the result equivalent to having a 2-micron defect in the sample because you've now included that defect into the loop. Having this built-in defect is really handy because it eliminates the need to create defects in the actual test samples. Intentional defects from laser drilled holes or sealing wires into the closure, they have some problems, and many sample types are not suitable for microtubes or microcapillaries in this test because the fixtures are so custom fitted, there just isn't room for them. So this is a feature we really, really love about the instrument. The CLO is our positive control for the test, and we generate a CLO value by running the master with the CLO switch turned on. This is done with every test set that we do, so we have a flow rate for a defect of known size in this specific test system. Test methods control how the test works. All methods have the same series of steps. These include pre-evacuation, evacuation, pre-stability, stability, pressure checks, and leak checks. The timing for each step can be changed in the individual methods, as well as the limit values. In the slide here, we have a picture of an example for a vial method. The vial takes about a minute for this whole method to complete for one sample. Different sample types and sizes may require adding some time here, or subtracting some time there from some of the different steps to create a suitable test method. For an inline manufacturing mass extraction test setup, where you have fixtures that are specifically built for a single sample type, you can optimize these methods to run in just a few seconds. But we opted for a longer test method so we can use the same method for a wider variety of test samples. So how does the method work? Well, to begin with, the instrument draws a rapid vacuum as part of what it calls a gross leak check. This is the 2.3 seconds in our vial method example. If there's more free space in the chamber, or you might have trapped air in the sample, then we may want to make that time a little longer. If the vacuum reaches stabilization before that time is up, then the test will progress to the next step. If it doesn't reach stabilization, then the test terminates. This is designed to protect liquid from getting out of these defects and entering into the test system. Remember, this instrument is very sensitive to moisture, and moisture has mass, and therefore it's interpreted as a leak by the instrument. So if we get liquid into the system, we have to purge it out before we can continue testing. The next leak check is called a large leak check. This is, again, a step mainly designed to protect the instrument from moisture contamination. Then we have a stabilization phase. For our vial example, this portion of the test, it represents about half of the total test time. Then we go to the final part, which is the fine leak check. This is where we're looking for those defects down to 2 microns or 5 microns, depending on the test method. For the fine leak check, the mass flow is diverted through the IMFS, or Intelligent Molecular Flow Sensor. The IMFS is a super sensitive detector that was developed by ATC to measure mass flow in very, very small quantities. The IMFS can measure very minute quantities, and that is really the reason why this test is the most sensitive on the market. In fact, ASTM F3287, which is the standard test method for non-destructive detection of leaks in packages by mass extraction method. That's the ASTM standard for mass extraction. That says that mass extraction method is capable of detecting leaks down to maybe 1 micron in some test configurations. Again, we've chosen 2 micron tests so that we don't have to optimize everything quite as tightly as you would need for the 1 micron. The IMFS records the final mass flow at the end of the test. Then this value is compared to the pass-fail threshold for the value for the method. If you're over that pass-fail threshold, then you fail the test and it marks it as a fail. And if you're under the limit, then it marks it as a pass. So where does that magic pass-fail threshold come from, you may ask? Well, there's no one number that's appropriate for all tests, just like there's no leak rate that equates to the same defect in all test systems. So we have to determine this value through validation of the method with the sample type we're looking at. For the validation, we'll need a set of non-leaking or good parts. And these good parts are tested with the method, and we get those final flow measurements. Then we test a corresponding set of known defect parts, and we get those values. We usually get our defect parts by running the good part samples with the CLO on to simulate a defect of a known size. Then we take these 2 sets, the good parts and the bad parts. We statistically compare them to one another, and we choose a value somewhere between those sets and calculate that as the pass-fail threshold. There are several approaches to doing this. It can be done either as a safety factor, say 2 or maybe 3 standard deviations above a good part average, or maybe 2 or 3 standard deviations below the bad part average. At any rate, it's somewhere in the middle. Now, let's go over how a typical test would be run. So first, we would select the chamber, the master, and the void fill that most closely represents the test sample from our library of accessories. Then we would pick the test method. As we talked about earlier, the methods are customized for the sample type. So if our sample is a small vial, then we pick the method that we have validated for vials. The first step in the test is to make sure the instrument is free of residual mass. Remember that the mass in the system will look like a leak to the instrument, so we have to verify the system is clean and dry by running the master. We know that that master is solid metal, it can't leak, so if the master fails the test, then we need to clean the system. Once we have the master passing, then the system's ready to go. Next, we run the CLO to determine a final flow value for a 2 micron or 5 micron leak. Again, the leak size depends on the method we're using. The vial method is validated for a 2 micron leak, so we would run the 2 micron CLO. And then lastly, we would run all of the test samples. Here's some graphs of some typical test data. The flat part at the front of the curve is the gross leak check. The larger of those 2 peaks that follow is the large leak check. The long flat line is the stabilization phase. Remember, that's about half of the test time. And the rise at the end is the fine leak check. The CLO value that we have labeled there is about 12, and it's a 2-micron defect. The passing samples all have values of 2 or less. The calculated pass-fail value for this method it's around 5, 5.5. So you can see that this value is somewhere between the good part average and the defect part. And you can notice the difference that you would see with a 2-micron defect versus non-leaking samples. It's pretty obvious. The final report would contain the critical method parameters. That's based on the standards requiring us to report those. And it needs to include the pass-fail threshold value and the pressure limits and some timing steps. The final flow values and the corresponding pass or fail result is given for each sample in the results table. We also report that CLO value, so you can compare it to your sample result. And this slide here shows what maybe the data for that graph that we just looked at would look like in a final report. So what are some of the most common questions that were asked about this test? Question number 1, how many samples do I test? Well, that's the question we get asked about almost all of our tests. The standard, it has no specific quantity to test. So that means it's left to each company to determine an appropriate sample size. This is usually done by statistically based sampling plan based on a few factors such as risk and lot size. If you need any assistance with sample size justification, that's another relatively new service that our Nelson Technical Consulting team is offering. So you can contact them for help with that. Question number 2, what samples are suitable for this test? We have validated methods and fixtures for small vials, glass syringes, and auto-injectors. We've tested some small screw cap containers as well, though these are not usually designed to the same tolerances, and they probably do better with a 5-micron method. In short, if it'll fit into one of our test chambers and it's a rigid sealed container, well, there's a good chance that we can test it. We'll be evaluating expanding the method in the future by adding some different chambers, maybe even a larger chamber for bottles, or we might expand into IV bags. I know IV bags aren't rigid containers, but ATC has published an article saying that it's a possibility. Question number 3, how long does the test take? Final report for typical mass extraction test is generally issued about a week or less from sample receipt, depending on the current workload in the lab. The test itself only takes a couple of hours, but it takes a day or 2 to get from receiving to the lab, and then a couple of days for data review and final report generation and report review. Question number 4, what about labels? Some labels, particularly cellulose-based labels, will off-gas under vacuum and cause a false fail during the test. The detector is picking up the mass from the labels and not a leak from the sample. There are a number of labels that don't off-gas, and those are acceptable to leave on the samples. But if the labels are causing a problem, then we just need to remove them before testing, and there may be an additional cost to removing labels. Question number 5, do I need to send defect samples? Well, no, you do not. The calibrated leak orifice is used to simulate defect parts, so sending out samples for laser drilling is not required. ATC incorporated a leak orifice into the test system to save people the headache of making defect samples. We use the CLO for method validations, and every routine test sample includes a CLO value, showing how that flow value would be for the stated defect size. Question number 6, what do I do if my sample fails? Since the test is non-destructive, we're able to do confirmation testing on the original sample. The master is run after any failure. If the master shows a leak, then the problem's fixed and the sample's retested. If the master passes, then the sample's retested to confirm the failure. That way we know that the failing sample is due to an actual leak and not a problem with the system. If you run into a situation where most or all of your samples are failing, then your sample may not be compatible with the test method. And in that case, we can try altering the method timing steps a little to achieve a suitable test method designed for your samples using maybe a method with a larger defect size. So that wraps up this webinar on mass extraction testing. I hope that we were able to demystify the test for you. It's kind of new and people have a lot of questions about it. I hope we were able to answer any questions you may have in the webinar. We are really excited about this test method and the advantages that it offers us for CCI testing. If you have a vial, a syringe, or an auto-injector type product, we'll hope that you consider mass extraction for your CCI needs.